Okay, so good afternoon and welcome back to this third session of the workshop. I'm Daniel Merzi from University of Leeds. It's a great pleasure to introduce this last session consisting of 3 talks of 30 minutes each. And it's a great pleasure to introduce first Professor Kay Chen from the University of Liverpool, who is a distinguished professor in various aspects, especially image analysis, boundary integral methods, and he has collaborators throughout the world, well-known person in the field. Okay.
Right, good afternoon, everyone. Thanks for the introduction, and it's a pleasure to give a talk here about some work I've been doing recently on restoration image, which is some old topic. If you haven't been to Liverpool, here it is, right in the middle. If Scotland remains, we'll be still in the middle. Otherwise, we'll be in the north. So in my research center in Liverpool, we do several aspects of imaging processing. Denoising, deblurring are the fundamental, like the first task you would meet in image processing. And other things like inpainting, segmentation, code registration, we've been doing a lot lately with applications mostly in medical imaging. So today I want to talk about some new work, mainly on blurring and with bit noise. Okay, so I don't want to hold you too long to say what I'm going to talk about. I'm going to show you the results. This is the main model I'm going to talk about later on. It's a generalization of the TV model. This is to restore the blurring kernel H and the image U, given Z as the image. So it's a double kind of TV. I'm going to show you why do I need to talk about it. So the final result will look like this. Given received data like this, we can restore the image like this. And then also for a different case. Okay, I'll show you what's like, but I need to go through the details. Okay, my outline will be in 3 parts. First of all, I just go through the simple stuff, the non-blind deblurring model with the Gaussian white noise, and then the blind deblurring model. And I talk about why we need transform models and to impose some constraints. Okay, let's talk about the easy one. What is blur? Blur is easy to explain. It's something you can't see very well. And along with the noise, sometimes like this one, we are talking about this retinal imaging for the human eye. And the idea is you want to see the blood vessels. That's a good one. You can see, the doctor can see what's going on. The vision area sort of in the middle-ish with the pointer here. So the vision area about here. And then for these are sort of reasonable, good, fair. Eventually you can't see anything with you can't process using any techniques with segmentation, whatever. Just you're totally gone. So this is one of the real life challenges. We haven't solved it yet. We are working towards, but this is associated with the diabetic patients. So like it's a very responsible topic if you think about it. We still can't find a solution to unblur this thing to see whether blood vessels are there or not there. So it's a bit tricky. Okay. Right, and what is blur is normally considered as a convolution with a true image, but with something. Here I look at some simple examples. So some with very little blur here on the right, and a bit more blur different types. And especially this one in the second column, that's a really tricky one to do even today. Right, and then I want to show you some of the mathematical blurring kernels. So here I'm showing this like a small Gaussian here. Okay, plot the image like a circle, and then plot a 3D mesh plot. It's a bigger blur, and this is like a motion blur with a constant. You don't know normally. If you don't know where it is, it's a bit tricky. And this is also motion along this diagonal, and these are corresponding images. So after blur, you see all these things. So one of the difficulties is we don't know which type we're talking about. Given an image, just like one of these here, okay, and blur it. show me the true image. Okay, it's a bit tricky. Right. And standard non-blind model, it's inverse problem, definitely. Okay, we've seen this formulation a few times today. So you're given image Z with blur in it. You assume it's convoluted with some kernel K, and we're looking for the true image U. And you need to regularize this thing, otherwise it's not unique, and you may get not meaningful results. And the total variation is a good one for certain kind of images, and you end up with a PDE like this. So it's a linear operator here, and then this is the nonlinear part, total variation, and this is the known. Okay. And then I wouldn't talk about the numerical results. There's several ways of doing this, and then that linear algebra side can be still improved. But if you look at the results, given some suitable choice of that parameter, this Mr. Alpha here, if we choose a suitable alpha, the results are pretty good if we know the kernel. Right, I have a different type of examples here. So I have the true image here. This is a blurred image with a given blur. I know whether it's Gaussian, motion, whatever we construct it. And if we use this TV model, it's sort of okay. But you may say staircasing and so on, you can improve with different regularizer, that's sure. But at least this framework works nicely if you know the blur. And with the color case, you can do it as well with this kind of thing. This is, I think we did using the channel by channel for the coupling the TV, but it's not the best way, but still. So that's original image, blurred ones, and restoration. So that's a good story. What's the problem? The problem is how to choose this alpha parameter. So all these ones were tuned to give best results, like a bit cheating. But we want to do it automatically so that these guys are reasonable. So we done some work. I want to show you briefly what they are. I'm looking at this general model. So this is like some power of a gradient. If p equals 1, the total variation of p can be 2. And some people look at sparse representation. P can be fractional, say 1/3, actually pretty good, or half. But here I'm looking at p equals 1 case and q fitting term. Also, we can play around with the semi-norms. Okay. So the one I talked about earlier with Bregman, I think that's a nice way to improve. With Bregman, you notice the speaker didn't talk about the choice of alpha. Actually, Bregman got this nice way of not worrying about alpha. What's going on here was with Bregman, normally start with the large alpha, your image is blocky, and then this procedure eventually correct itself. So therefore, the alpha choice is not so serious with Bregman. If you say I don't do Bregman, I just go for this formulation, try to solve for fixed alpha. Really have to choose the best one. Otherwise, the result can be really bad. And that was early work by this Italian colleague, Lande, visited their group in Bologna. Using the KKT system, try to solve it for this parameter. Treat it as unknown and solve for it. Because of optimization, you just plug in the alpha as unknowns and try to solve it. And then later on, we some work we did here. I'm going to talk through briefly how to choose this one without solving for the alpha, using some sort of semi-analytical way to do it. And then when my friend Raymond Chan had a paper, they use prime dual formulation, this DP. The DP means if you sort of converge within some sort of known threshold within a noise level, you stop. Okay, so let me show you another open problems I find really challenging. And some of the non-convex optimizers are really good, give very good results. But with a suitable choice of the coupling parameters, if you don't know how to choose them, there's no way of doing them, because we rely our analysis on convexity. If they are not convex, like a high order, no, that's really tricky. I think there's still something interesting to do. Right, the work I've been doing, I changed the notation a little bit, so that the total variation operator is a standard ROF thing, and there's a coupling parameter, that's F, which is the fitting term. And then what we look at, if we treat this parameter, I called lambda now, previously called alpha. as this is normal sort of TV equation for this is for denoising, for deblurring, you can do it as well. And then you have this thing, this F. So you solve this one simultaneously, and actually there are problems because this sort of not well conditioned. You notice this regularization parameter epsilon. If this guy is really small, the convergence is a problem. Actually, that's a problem with the TV equation. We never solve TV by Newton type or quasi Newton because they think singularity is so strong we can't use Newton at all. And then Landy exactly used Newton. That's why she took a very large epsilon, get reasonable results, but I think that's not ideal. So what we do, we use, as I said, we use semi-analytical ways, try to say, let's somehow avoid solving this thing in a coupled way. We still solve it in another way. Okay. So I'm going to show you I don't want to hide the results. I just want to show what we got essentially to say. We look at this behavior of this functional with the two unknowns. So for each lambda, you get u. That means lambda u depending on lambda choice. So essentially, we are later all the property rely on this f. F, is superficial depending on u, but it's depending on lambda, and then you can show this thing is monotone in lambda. If you know the guy is monotone, then you have a nice way of find the best lambda. How? You want to drive this thing to be zero, or it's monotone. Bisection is an easy way to do it. So that's exactly what we did. Okay. So how do you develop the theory, and then you can show these are standards, not too hard stuff, just using the convexity of this energy function, or you can show these equalities. Equality just suggests this guy is strictly monotone for positive lambda. And what else have we done? And then and from there, you can use the implicit function theorem to show you can find the lower limit 0 and upper limit say infinity. As the guy is monotone, you can locate this parameter nicely. And then you wouldn't need to read this slide, just saying how to do bisection. No, we'll teach this stuff. And you start with two numbers, small one, big one. You have different ways. Essential bisection, we can also use other ways of find this one-dimensional parameter. And then here we use multigrid. For fixed lambda, how do we solve this u? We use multigrid to do it. That's small detail. So essentially, we get a sequence. So we get all these pairs, lambda versus u solution. Obviously, you don't want to do too many steps. Normally, typically, like Bregman, 5-6 steps, you get convergence, and then you don't want to carry on. That's good enough. I'll show you some numbers. Right. So for this case, typically I do 4 iterations. So for this case, remember this epsilon choice? I was saying with the landed method, if epsilon is really large, say 1, 10 to minus 1, her method is pretty good. I find a sort of almost best parameter with a lot of quasi-Newton iterations here. And then find this quality. And then our thing take 4 steps, find similar parameters. But if this epsilon guide getting smaller, Newton, as I said, Newton pretty bad. And you see the true color for the nonlinearity, and then this thing not kind of converging. You can't find this parameter. Okay.
So you compute a set of minimizers.
That's right. You keep checking the f, this f thing. Where's the f? Yeah, this f function, which is fitting term minus the estimate.
You check if this.
Yeah, if the guy is near 0, if it's small enough, stop. Quite straightforward. Okay, so it's typical of 4 steps. You sort of stop, and then you find. And same. Also, we generalize this thing to deblurring. Deblurring the same function. Also, you have the fitting term and some estimate sigma. You can show the theory. Just generalize this case also. This was done with a colleague from Bologna, Alina and Fabiana. And then what happened was, so here we done plot, actually didn't plot against f, we plot against this SLR, which is not part of the theory, which is essentially this thing. And then, so you can see our best choice for 2 cases. One case we stop here, and the other case stop here, and it's low noise case. That's the other motion blur, we stop here. So almost the best precision. Okay. So that's the best choice. So I don't want to hide this anything. I was just saying, we use a lot of convexity of TV functionals. Without convexity, we can't do it because there are a lot of problems we like, a lot of models we like. We can't find this best parameter. Right. Any questions? Right. Blind models. That's the one I want to reach better. This is the main thing I want to talk through. With the blind, what happens? Same TV model we want to look. Obviously, we can look at high order regularizers, but I think it's, let's get this one done first. What's the task? We don't know the yield. We don't have a fitting term here. It's very easy. We don't know the blurring kernel. We don't know the function. We don't know anything. So we, so natural thing to do. You just you regularize both. This is done by Tony Chan and CK Wang in 98. 99-ish, they published a couple of papers. You would think you find a couple of the TV equations, you get on with it. You know what? It doesn't work at all. Why did they publish the paper? Because sorry, I don't want to put too negatively. They published two numerical tests in the paper. One's not this satellite, different satellite, simplified satellite. They give reasonable results, not very good, not as good as what I'm going to show you. What happened was we can't find another, put it bluntly, we cannot find a third example, simple example, where this thing works. It just happens. They find these ideas, in the late 90s, really attractive, double TV. It's reasonable, but it doesn't work very well. Okay, actually they said in the paper it doesn't work for Gaussian noise, only for motion, very modestly, but even for motion there are problems. But it turns out a lot of constraints they haven't talked about. What are constraints? You can see a lot of assumption on this H. For U, we don't care. U is the smoothness, which space you're looking at. This guy might be symmetric, for example, around the 0 point, and the thing must be added up to 1. That's all normal. These two guys must be positive. You see what's going on with restoration, like the model we've seen this morning. If we use the negative for the image, you can try to say, okay, just a couple points, no one noticed, that's fine. We plot, you can't see anything. But if H is negative, you do convolutions, you destroy the iteration completely. So after 2-3 iterations, you get a completely wrong result. So you want H to be non-negative really seriously, not kind of say, okay, yes or no. So we found that's exactly what happens. So these are the other satellite we done with this image. You get some ghostly reconstruction. Actually, you might say this, we lose more features than the blurred image. You see, okay, that's not good at all. This come to our work. We say, okay, how do you make a thing positive? And then we have this model again, and then we consulted several people to see what's happening. In the last SciEM meeting in where is it? Philadelphia. I talked to a couple of senior colleagues. They were saying, "Oh, you're working on that. You're actually in trouble. We haven't seen any new result last 15 years." Anyway, and some people suggest, "Why don't you make it positive like this? Don't rush to solve H. Just do a transform like this, and then your new system will be in WU, say." And then for any W you get, you do the transform, you get positive. I said, oh, God, it's so easy. Why didn't we think about it before? But you can immediately, when you sit down when you find excited when you talk, after talking to them, when you do this, you say, I can't even start, because you give it some estimate of initial H. H normally decay to 0 very quickly. At the most pixels, H is 0, you take a log. First hurdle, you can't even initialize. And you say you take a threshold. So where is 0, you input a huge number to the W for initialization. And then we try, it doesn't work very well. It's a beautiful idea that doesn't work. It's just a pity. So we said we didn't give up on this idea. So what I propose showing you is a modified version, where this is like exponential here. We make sure this guy is bounded, it never reaches infinity. So this is like a heavy side in some sense, yeah. So between 0, 1, and then, or you can scale it, so it's in some bounded numbers, inverse also bounded. So that's the sort of thing we propose to do. So the same idea, people suggest to us kindly. And then actually the exponential thing works for us in other subject, not here. And then let me show you the small details. So this is plus. So we can replace h by the transform this t thing. And then actually we did it also for u because it doesn't cost a lot. So we do for h with the t the similar transform. Actually, slide should be t1, t2. You could choose this parameter differently. So what's the catch? The catch is it's a linear filter. Now we make it nonlinear just to achieve positivity. So how do we solve this differential equation? We say, okay, we are asking for trouble. The TV part is fine because it's nonlinear anyway, make it more nonlinear. But this one make it impossible. So this is our first, I call model 1. We will say, okay, it's nonlinear, let's linearize this thing. So you notice all the thing hiding here. Take a linear part of this, transform the Taylor expansion, keep a linear part. So therefore, this thing is essentially still a linear kind of filtering. But anything nonlinear, just shuffle them into the Z bar. It's a global inner outer iterations. It's okay. At least that's some sort of fixed point iteration. It sort of works. It's not fast. So we sacrifice sort of efficiency. Just to achieve this quality. And then we get another version. Version 2 is sort of interesting because we are saying, okay, this is the splitting idea. We were saying, don't split these guys. They are good partners. If you make a nonlinear, they'll be nonlinear against nonlinear convolution. It's really impossible. This is like prime dual in some sense. So we keep the original HU variables. You see this thing? It's typical splitting. So if you want to impose this, but don't put it in here, you put it here. And then this is sort of Lagrangian formulation. And the error guys, you don't care about this regularization. This total variation, that's fine. So that's a very naive idea. And then you get these equations with the new, with more unknowns. But it's all sort of to deal with this fitting term. So we still, it's back to the original formulation, double TV. For this sort of non-local operator, we keep make it linear. For the hard bit, it's non-linear, it's doable. Now let me show you the results. The results looks good. This is for the motion blur. And what we got? We compared with something. So if you look at the blurred image, 2 cases, then this ROF. ROF is double TV. You say, remember I said ROF doesn't work. Why does it work now? We use a clever thresholding within the iterations. Not threshold negative. It says it's more than 1/3 with taking out 0 because otherwise it affects the whole thing. So this is not mathematical. If you think about it, you want H between 0, 1, and 1/3 is off. But it gets something reasonable and superficially. And the Vogel method have another way impose positivity. This active set method, and this is the transform thing. They look visually look very similar, but if you look at numbers, they are different because with those methods, the ranges are different, and the visual looks different. So if you look at what you're looking at, look at PSNR. So our quality clearly is much better. So this is heavy 2 stuff, our stuff. So against this is for motion blur against the Vogel, the others, CPU similar. Here I'm showing the best method. The method 2, the one with the prime dual idea. Otherwise, we can't compute the speed. Okay. This is with the Gaussian blur. Remember I was saying in a Chan Wang paper, it says it doesn't work with Gaussian. They just tried it, but this thing works equally well for Gaussian with this transform. So that blurred RF will go. And then again, the numbers looks pretty good. Right. So this reaches the 2 images I was talking about earlier. So for this case, it's given an image like this, and then you can restore them without knowing what's going on. Right. So what I talked so far are blind models through achieving positivity. We sort of make the Chan Wang model achieve their original aim. They didn't manage themselves. But this because with the double TV, obviously that's okay. in terms of complexity, with this our new preferred method, we have 4 variables. That's like a lot of work. So and then we say, let's make it easier. This is semi-blind, parametric. Suppose the Gaussian type, with the Gaussian kernel, there's only one thing. So it's a zero mean. There's one sigma parameter. You say, why don't you try so hard with finding one parameter sigma? So we said, let's do that. So you specify which type of blur you're looking for. Go for this unknown sigma, which is semi-blind, not totally blind. And so what's going on here? So that's the thing. You're looking for so the center in the middle, and then you're looking for the best sigma which does this fitting. Okay, so this is our basic version 0. You plug in this known expression into here. You try to restore here. We put our positivity phi thing here, and then no regularization on sigma. We solve just a scalar non-positive number, and then it works well for some cases. There are some problems. What's the problem? The problem I said I didn't show the image. With no noise, this works really well. This parameter, this Gaussian type, you try to restore this blur by the sigma and the image. It works for. With a bit of noise, it doesn't work very well. So and then we say, okay, let's make it more sophisticated. How do you make it sophisticated? You regularize sigma, in other words, regularize each sigma thing, and then you do that. You improve a little bit. Okay. So and improve a little bit. So just this slide just showing this is the regularization for the sigma term for the each sigma. This the other the image stuff, and it works well. And then if you take a sigma equals 0, you get the wrong results. So here we have because they're all test problems. We have 5.2, which is the true solution. If we take a smaller sigma alpha, if you take a 0 alpha, it doesn't work. Take a 10⁻³ works, but it's a bit fiddly. and then we say let's find something better. And then this is the idea, like, because we said how do you make a noise image noise free? You're splitting. So what do you see here? Forget a small detail. You're saying previously we have convolution match this given data, which is noisy. This model with the parametrics doesn't like noise, not at all. So what we say is, okay, let's put a V into this fitting. So the noise goes through this square thing, like denoising. You try to construct something smooth against this Z, and then plug in here and deblur here. Just make the parametric model happy. And it works. Works very well. So you have a more equation stuff, and then I just want to show you the results. Right, just time. And then you have the received image, which is the one here, 3 cases. And then this is the denoise V through this splitting idea. And then this is deblurred ones. Yeah. So it doesn't care about this noise. Right. Let me reach my 30 minutes. So what have we got here? I was saying for standard deblurring, no blind, we have a very effective method algorithms, and the further improvements like regularization, fast implementation are possible, but there are good ways of doing them. For non-TV type high order method stuff, we don't know how to choose the parameter yet. For the blind case, positivity seems essential. So, through a transform thing, we can achieve the full potential of the original Chang-1 model. For the parametric case, we make it much faster, but have less unknowns. And then the splitting idea seems the key. And there are lots of problems with optimized parameters we haven't looked at. Right, that's it. Thank you.
A comment? Yes.
So for your blind deconvolution method, I wonder, have you ever looked at the quality of estimating the blurring kernel? Because for some applications, this can be also quite important.
Okay. Quality, you mean to see the profile, like to see what it looks
Yeah.
like. Yeah.
So what's the blurring kernel? What?
For here, we basically look at a motion blur, like I was showing earlier, like a cylinder-like,
Yeah.
constant in the middle and then zero outside. Or we look at Gaussian, yeah, Gaussian profiles. For these two, it works very well.
I mean, when you do it blend fashion, so you not only estimate the image itself, but also the kernel, right?
Right.
So I wonder how accurate you can estimate the kernel.
Good question. In other words, go beyond the traditional type. Yeah, do a mix to see, because this model theoretically doesn't care, especially the non-parametric case. It doesn't know or doesn't care only through regularization. In that case, I think you're right. I think we can, for the test problem, just plug in any z and then see what comes up. Good suggestion. We haven't tried that. we are happy because the paper was designed for motion blur. It didn't work very well. It says not for Gaussian, but make a Gaussian also work. We sort of happy with the low bar. We say okay, we're happy already. But you're right. If you go a bit further, because there's nothing else suggests we need a special H. We just want a minimum total variation. So it's.
So I guess the question is more how well the reconstructed kernel fits to the real kernel.
To the real kernel.
To the real kernel you planted, which is not one of these types. We haven't tried. We hope it should work, but haven't. Okay.
So how would you choose two parameters, then alpha 1 and alpha 2? Just
That's a bit tricky because this thing is with one parameter is convex, jointly not convex. It's a bit tricky. So the old theory doesn't work. So we need somehow work harder on this. Yeah.
okay. So thank you very much. Yeah. For,